In this video, I'm going to talk about what it means for a function to be continuous on a closed interval. We already discussed the definition of continuity at a point, which I will remind you of in a minute. We also talked about continuity on an open interval, and now that we have left and right-hand limits, we can also talk about continuity on a closed interval. So a function f is said to be continuous on a closed interval ab if it's first of all continuous on the open interval ab, and the limit as x approaches a from the right equals f of a. So in other words, in symbols, the limit as x approaches a from the right of f of x is equal to f of a. And furthermore, the limit as x approaches b from the left equals f of b. So the limit as x approaches b from the left of f of x is equal to f of b. Alright, so see that this definition sort of makes sense, because if we're talking about being on the closed interval, the limit as x approaches a will not exist because we can't approach from outside this interval. So we can't approach a from the left because the left is outside this interval, but we can approach a from values bigger than a because values bigger than a are inside the interval. So we're going to just restrict that at the end point of the interval, we're going to approach from the direction inside the interval. So if I approach from values bigger than a, then I'm inside the interval. And if I approach b from values less than b, I'm again approaching from values inside the interval. And to make the function continuous, remember that the limit has to exist according to our rule, and it has to equal the value of the function. So we simply state that the limit as x approaches a from the right of f of x equals f of a, and the limit as x approaches b from the left of f of x is equal to f of b. So remember that our basic definition of continuity at a point, we would say that a function is continuous at c if 1, the limit exists, 2, the function is defined, and 3, these things equal each other. Okay, so if these three conditions hold, we say that a function is continuous at the point c. It's continuous on the open interval if it's continuous at every point within that interval. And now we have the additional information that it's continuous on a closed interval if we approach the left endpoint from the right and get the value of the function, and we approach the right endpoint from the left and get the value of the function. So that means if we look at, for example, the function f of x is equal to the square root of x, and we want to discuss the continuity of this function. Well, first of all, we know that this function is defined on the interval from 0 to infinity. Okay, so we have the condition that f of c is defined on this interval. So now the question is this function actually continuous on this interval? Well, the limit as x approaches c of f of x does exist for all points on the interval from 0 to infinity because of our definition of the limit of the square root function. Remember that if we said the limit as x approaches c of the square root of x is equal to the square root of c for all c strictly greater than 0. So we have that on the open interval from 0 to infinity, the limit exists and it equals the value of the function. Alright, so now that we have this function continuous on the open interval, we can decide whether it's also continuous, in this case, on the half-closed interval. So to decide if it's continuous at 0, we have to look at the limit as x approaches 0 from values bigger than 0, okay, because we have to stay within the interval here of the square root of x, and see what this is equal to. Okay, well, now we know that if we're approaching from values bigger than 0, then we are within the domain of the function, and so that limit will actually exist coming from the right. Even though coming from the left it does not exist, coming from the right it does exist, and it is actually equal to the value of the function, which is 0. Okay, so we've satisfied the condition here for being continuous at this endpoint, and therefore we can say that this function is actually continuous on the interval from 0 to infinity and including the value 0. Alright, so now we're going to look at an example of another function. Let's say the function f of x is equal to the square root of 9 minus x squared. And we're going to discuss the continuity of this function. Alright, so first of all, again, we have to decide what the domain of this function is, and remember that since this is a radical function, 9 minus x squared must be greater than or equal to 0. And the only way that this is going to happen is that if x is between -3 and 3 inclusive. Okay, because if x is -3 or 3, this will equal 0. But if it's bigger in absolute value than 3, like for example 4 or -4, then this will be negative, so that's outside of the domain of the function. So x has to be between -3 and 3. Alright, so here is our domain, the interval from -3 to 3. Okay, this is a closed interval. Now let's determine if this function is actually continuous on its entire domain. Alright, so again, because it's a square root function, we know that the limit as x approaches c of the square root of 9 minus x squared is equal to the square root of 9 minus c squared, as long as c is actually strictly between -3 and 3. Because remember, if that makes this thing 0, as we discussed previously, the square root of 0, the limit will not exist. Alright, so we have then that this function is continuous, at least on the interval from -3 to 3. Alright, because the limit exists and it equals the value of the function on this interval. Now we need to look at the endpoints of the interval. So we also have to look at the limit as x approaches -3 from values bigger than -3. And we also have to look at the limit as x approaches +3 from values less than +3. Because again, remember that we're approaching these endpoints from within this domain. So if I'm approaching -3, I have to be approaching from values bigger to stay within the interval. And as I'm approaching +3, I have to be approaching from values less to stay in the interval. Okay? Now, because I'm looking at one-sided limits, in this case, the limit does exist because I'm coming from within the domain of the function. So this limit exists, and it's actually equal to the square root of 9 minus -3 squared, which is equal to 0, or the value of the function. And the same thing happens here, because now I'm approaching 3 from within the domain of the function. And since I'm within the domain of the function, this limit is also equal to the value of the function at that point, right? So since the limit from the right at the left-hand endpoint equals the value of the function, and the limit from the left at the right-hand endpoint equals the value of the function, we say that this function is continuous at these two endpoints of the interval as well, and therefore the function f of x equals the square root of 9 minus x squared is continuous on the closed interval from -3 to 3.